Okay, so you got the Green's theorem. What works due tonight at 7. So let's talk about this problem. The first thing is I posted an announcement about this notation that's all throughout this homework that I've never used in class. And that's this line integral p dx plus q dy. That's throughout this homework. So that's simply another mathematically equivalent way of saying f dot dr, and it's because this is a dot product of p comma q, vector pq, and vector dx dy. So that's pq dot dx dy. Well, that's our vector field f, and that's dr. So whenever you see this p dx plus q dy, or this form like this, it's mathematically equivalent to f dot dr. And I posted that Monday. I hope you caught that announcement. But I just have never used this. So this is a line integral through a vector field. We've always called it this. We never called it this in class, but it's still a line integral through a vector field. Any questions on that? Okay, so this one is asking about the non-closed path ABCD. So from A, traverse to B, traverse to C, traverse to D. And so when we think about Green's theorem, we know Green's theorem says that the circulation integral, so C being a closed path, of f dot dr equals the double integral over the enclosed region of this thing and we said this is a fundamental theorem, right? This is a fundamental theorem of calculus because this is something of a rate of change, right? Something of a rate of change of that. This consists of P and Q. So this is like the rate of change of that. And it's like we're accumulating all these. It's like we're accumulating. This is actually kind of a rotational bit of change. This is like a rotational bit of change for a little bit of our region. So we're accumulating all those little rotational bits of change throughout the region. And when we do that, that's equivalent to the kind of the net accumulation around the boundary. So that's how that's like a fundamental theorem. And so does Green's theorem apply to this? Well, this is not a closed loop. This C from A to D is not a closed loop. How would it be a closed loop? So this thing, so it's like our integral from A to D of f dot dr. And then what else would we need to close the loop? Yeah, the integral then from D to A along here. So the sum of those two would give us a closed loop around that, and then that would equal the double integral over D of qx minus py. So in this problem, they're asking you to find this. So because it's not a closed loop, you might think, oh, I can't use Green's theorem, but so this is kind of my hint that you still could use Green's theorem to get the value of that integral that goes just from A to D. If you kind of see what I've said. So that's a hint. So this whole thing that's your closed path. The one they're asking for plus the last little leg gives you a closed path that would be equal to a double integral. Okay. So that's just a little hint in your homework. All right. So we're talking about Green's theorem. Let's look at conservative vector fields and stuff. Let's look at an example here. Any questions before I erase that? So we did those examples. Okay, so let's look at this one. here's a vector field. That should be chevrons, not. Okay, so we got this vector field. Minus y over x squared plus y squared is the x component of our vectors. X over x squared plus y squared is the y component. Remember vector fields, what they assign every location gets assigned a vector. That's what a vector field is. Every location, so every location xy gets assigned a vector, and that vector depends on the location, right? Your x component depends on location. Your y component depends on location. And so this is our PQ. This is our PQ. So, question, is this conservative? This is a conservative vector field. How can we check to see if it's a conservative vector field? We kind of got two different approaches to figure out if it's conservative or not. All right, Clairaut's theorem, right? So we can look at second derivatives, right? The other way we check is just we kind of just try. We just like try to find the potential function and see if it works. So Clairaut's theorem, so rather than take the time to do this, because when we do Clairaut's theorem, we're going to use quotient rule, right? We got two fractions there. So the first one we're going to take the derivative with respect to y, so p with respect to y, and then the second one, q with respect to x. So I've kind of just, here's q with respect to x, quotient rule, and p with respect to y, quotient rule. And when you simplify those, you get y squared minus x squared over x squared plus y squared squared. And you get that for both. Conclusion? Conservative, right? So we got our second derivatives are equal, so we got a conservative vector field. So here's two paths in this vector field. I got a square path from 1 to 2 and up to y equals 1. And then I got the unit circle. So what do you expect for, what do you predict for these two circulation integrals? The path of the blue square and the path of the red circle? 0, right? Expect 0. Okay, so here's the, you're not going to, don't copy this down, but here's the math for the blue square. We got to do 4 different line integrals. Okay, don't copy this down. But from 1 to 2, this is the bottom. So from here to here is actually 0. Up from here to here is probably about 0.46. That's the second one. Then went back this way. And then we went down this way. And then you add those 4 values up, add up the 4 separate pieces, you get 0. Check, right? All right, let's do the, so 0. That circulation integral is 0. Let's do the circle, the unit circle. So for the unit circle, what we need to param, so we're going to call that C2. Right here. First thing we need to do this line integral is? What's that? We need the curve in terms of t, right? We need to parameterize the curve, so we'll call that R2. Unit circle, best parameterization is? Cosine and sine. Perfect. Okay. And then we're going to do, so now we're going to set up the line integral of f dot dr. Well, let's do our other, let's do this notation, just for kicks here. That's the same as f dot dr, right? That's what we said. And so we need p in terms of t. What's p in terms of t? Negative sine over x squared plus y squared. Cosine squared plus sine squared. 1, that's nice, okay? dx, right? So that's going to be, this is our x. It's going to be derivative of this times dt. Negative sign. We'll pull the dt out at the end, okay? Plus q is x over x squared plus y squared. It's going to be cosine t over 1 times dy cosine. And that all dt. And that from 0 to 2 pi. Okay, 0 to 2 pi. So what do we got? Sine squared plus cosine squared. 1. So I end up with integral 0 to 2 pi 1 dt. And because it's conservative, that equals 0, right? Is that right? What's that? Yeah, that integral doesn't equal 0. It was supposed to, but it doesn't. What does it equal? 2 pi. What's going on here? Did we make any mistakes in the integral? No. Our math is good. We got a conservative vector field, qx equals py. We made a closed loop in that conservative vector field. Everything we've learned should just say if we do everything right, we should get 0. But we don't. We get 2 pi. This is why we have math class, because there's interesting things, right? What's going on here? What's going on here? Anyone want to take a guess? Yeah.
Well, that's the area of the circle. Wasn't there like
well, it's a single integral. Oh, it ends up being there 2 pi. Oh, yeah, it ends up being the area of the circle. That's true. Okay, so we had to talk about a few other things, and then at the end of class we'll come back to this question. All right, so we're going to talk about a couple other things here, and make sense of all this. What's happening? Okay, can I erase? So that's what we found. Something's wrong. Okay, so let's talk about regions. Let's talk about what we mean by a connected region. A connected region. The idea is the region is connected if it consists of one piece. One of these is connected and one of these is not. Which one is connected? I even gave you a color prompt. Green light, right? Green light. D1, connected. D2, not connected, right? It's two pieces. Okay, the formal definition, so a mathematical definition would be that given any 2 points, A and B, there exists some path from A to B that lies entirely in D. So you can choose any 2 points, call them A and B, and you have to be able to find a path that connects from A to B. Is that true in D1? No matter what 2 points you pick? Yeah, no matter what 2 points you pick, you could find a path that lies entirely in D. Is it true for D2? No, because if you chose A over here and B over here, you could never draw a path that lies entirely in D. So that's the math version, but the general idea is one piece, right? One piece. Okay? Simply connected region. A simply connected region. The idea is the region is simply connected if it's one piece, because it's connected. And the simple part means there's no holes in it. There's no holes in it. Which one is simply connected? It might be harder. I didn't give you the green and red this time. I think you can do it though. Which one's simply connected? D2. Simply connected. D1 is not. Here's the formal definition behind that. Okay. Every simple closed path that lies in C that lies entirely in D. For every simple path that you could draw, it's like a little circulation within that's totally within your D. Every point enclosed by that circulation is also in D. So is that true for D2? If I make a circulation that stays entirely in D2, will everything inside that little circulation also be in D2? You see that? What about in D1? Does every circulation within D1 contain all points of D1? What do I need to do to show that's not true? Go around this, right? So there's lots that are fine, right? There's lots of ones that are fine. Like all those are good. But if I do this, if I go around one of those things, that violates this rule, because now there's points within C that are not in D1. So not simply connected. Okay, so any questions on connected regions? Simply connected region. So let's look at this in light of Green's theorem. Let's look at regions in light of Green's theorem. So here's a region. Is it connected? Yes or no? Connected. Is it simply connected? No. Right? It's got a big hole in it. So in order to kind of analyze this for Green's theorem, what we're going to do is I'm going to take a scissors and I'm going to cut this thing in half and move it apart. And I'm going to look at those two circulation integrals separately. So I'm going to use my positive orientation, which means I'm going to walk around so that the inside of the region is always to my left, right? So that's counterclockwise on both of them, right? So then so if this whole thing has a boundary, so this is a region D. This is region D with boundary C. Okay? And so this is still region D with boundary C, but it's just cut apart. So I'll call this one C, say 2, and this C1. And so do you see that if I were to do the line integral of C1 and add it to the line integral of C2, what would I get? Is that different or the same as the line integral of C? So what happens when I do those line integrals? Actually, she has broken it all the way up. Let's see. I want to break it all the way up here. So this is, let's go. C1, C2, 3, 4, 5, 6. All right, and what happens when I add all those up? When I add up C1, all the way to C8. So I'm going to add all 8 of those separate pieces up, and what will happen? What will I get? No, just focus on the line integrals. Don't relate it to region D. What will happen? So do you see that C2 and C5 will be equal and opposite? And C4 and C7 will be equal and opposite. So I'll just get C1, C3, C6, and C8. And so basically what that amounts to then is, what? So C1 plus C8 means do the counterclockwise loop around the outside. If you add those two together. And then C3 plus 3,6 means do a clockwise loop. And is that still our positive orientation? Going clockwise? How is that still a positive orientation for that inside loop? You see that the region is to the left? See? So C1, C8 give the outside loop positively oriented, and C3 plus C6 gives the inside loop still positively oriented because as you walk, the region's to your left. Does that make sense? So the boundary C, when I say boundary C, that includes the outside and the inside as two separate loops, are all part of the boundary. So we'll just reduce that to C. So C1 being the outside and C2 being the inside. So I'm renumbering now. We'll do C1 and C2. So using Green's theorem then means what? That if we to set up Green's theorem, what would the integral C be? It would be the sum of those two, C1 and C2. And then because of Green's theorem, that would equal what? That would equal the double integral of this qx minus py. It's like a rotational rate of change. It's like rotational rate of change. Okay, so everything's still good. So basically, this is how you'd have to apply Green's theorem to a non-simply connected region. Your boundary is split up into two, so then the circulation integral of the boundary would be the sum of two integrals like that. So then what if we had a conservative vector field? In a conservative vector field, what's true? So is C1 0 and C2 equal to 0? What's that? Just C2 is equal to 0. What do you think? Yeah? So each are equal to 0. Is that true? The sum of them has to be 0. So what we said last time was in a conservative vector field in Green's theorem, this is 0, right? And this is 0. This is 0 because you're going around a closed loop. It's 0, and then that's 0. So if the line integral of C is 0, does that mean the individual line integrals are 0? What does it mean for those individual line integrals? They sum to 0, right? And if they sum to 0, then what can you say about them? They'd have to be what? If they sum to 0. Equal and opposite, right? They're equal and opposite. So the line integral is still 0, but that line integral is split apart into two actually separate paths that have to have equal and opposite values, non-zero values. Okay, do you follow all that? Yes, please.
What if you just took C2 out and you just took the integral of C1? Why wouldn't that just be 0?
Because you don't get the whole boundary. C2 is just as much a part of the boundary of D as C1.
Aren't you in like a conservative vector field still?
Yeah. Right, but it's a closed loop around a non-simply connected region. You don't have, right? This is the idea.
Okay.
Because this isn't part of D. So because that's not part of D, C2 makes up part of the boundary of D as well, and you can't neglect it. But you're onto something. This was a great question. Okay? Is this what we've said so far makes sense? So we're applying Green's theorem to a non-simply connected region. It still holds. You just have to consider the whole boundary of D, which is two separate loops. So when you add those together, the total line integral would be 0. So back to our question. What did we get? We got 0 for that one, but we got 2 pi for this one. Anybody see what's going on now? Christian?
I guess at the point 0, 0, you're dividing by 0.
Okay, so he's on to something here. 0, 0. What's happening at 0, 0? Undefined, right? Okay, so how can we relate undefined at 0, 0? So that vector field is undefined at 0, 0. So it's like, how do we graph that? How do we graph that? Yeah. It's going to hit someone like a ton of bricks really quick. What's happening here? You have an itty bitty bitty hole right in the middle of D. What's that? Why are you saying that? So D, simply connected or not? It's not simply connected. There's a hole in it. It's small, but it's still a hole. It's really small, but it's still a hole in D. It's not simply connected, so what's happening here? So what did you say, Winston? You said? So if I were to do so basically, is C2, is it the boundary of D? There's more to the boundary of D than just C2, the unit circle. What's the rest of it? Yeah, so we need another little path. And which way is that going to go? Clockwise. We need another little path, and it's like infinitesimally small, right? So we'll call that C3. So we're going to find the line integral around the teeny hole in our region D. And what do we expect to get? If we expect to get negative 2 pi, and then everything's right in the universe again, right? Because then our line integral truly is 0, because it consists of the two different paths. So how do we do that? So we're going to go, we need to parameterize that path. Okay, so this is going to be R3. And now, so it's going to be cosine sine, but the radius is going to be really small, so we'll just call it capital R for now. So capital R cosine t, imagining capital R is really small, okay? Capital R sine t. All right, and we're going to do, so now we're going to go the integral around C3. This is a 3. is going to be f dot dr. F, same thing again, right? So f is going to be minus y over. So now I've got x squared plus y squared. What am I going to, if I do r squared cosine squared plus r squared sine squared, I'm going to get r squared. And that's my, what is that? That's p, so we're doing the comma. And then q is r cosine t over r squared dot dr. What's dr? Negative r sine t and r cosine t dt. Okay, did you see what I did? So now it's kind of like the same thing as before, but instead of radius 1, it's radius capital R, and eventually we're gonna make R be really, really small, okay? But right now R is just like smaller than 1, capital R. So what do we get when we do all that stuff? This should be C3. So we're gonna get negative sine squared. Looks like everything's going to go away and just get sine squared. Is that right? And then cosine squared. All the r's are going to go away. See that? And then now I'm going to go from what to what? Yeah, you could do that, or we could go 0, start at 0, and going around this way, we could end up at, if we're going clockwise, negative 2 pi, right? And what is it? And so now, but we need to, so capital R is still not small. I'm going to take the limit of that as R gets really small. So when capital R gets really, really small, what happens to that? Doesn't care about capital R. Has nothing to do with capital R. So you can make it as small as you want, and its value will still be what? Negative 2 pi. And that's what we were hoping. So what happened? When we first did this integral, we didn't do the whole boundary. We only integrated the outer ring, when we didn't see that there was another little teeny ring here, that was part of the boundary of D that we left off. When you include it, now what's our line integral? 0, right? Because we can add what we did before, the positive 2 pi, the negative 2 pi around the little teeny hole. And everything's right in the universe again. 0. Yeah?
Is there like some part of that area that's not in R2? Because just looking at an R2, it looks like you kind of have the same value because the size is so different. So does that mean like there's, I just don't understand visually how that works.
Well, when we calculated this 2 pi, it wasn't the area of the circle.
All right, it's the path.
Yeah, if it's a double integral and it was 1 for the integrand, then it's truly calculating the area of D. But that's just coincidental that we got 2 pi and that's the area of that circle. That's not a meaning for that 2 pi.
Yeah,
so is that, okay, yeah.
So like any closed path around the origin is going to have a line integral of 2 pi then?
Yes, that's good point, right? So yes, we could do squares, we could do triangles, and no matter what, we're going to get positive 2 pi. But that's going to be a big surprise because any line integral of any shape anywhere else always gives 0, right? Gives the same value everywhere. So now, yeah, it's for every time that you go around the origin, doesn't matter how you do it, you're going to accumulate. It's going to be 2 pi. So you can go around twice, it'll be 4 pi. It doesn't matter how you go around. Just like it doesn't matter what your circulation paths look like. Those will all be 0 as long as they don't go around the origin. You're not looking satisfied with my answer. Oh yeah, okay. Okay, other questions on this? Thanks, Mark. That was so cool. All right. Let's talk about, let's see. These questions. Let's see. Are these the right questions to ask? Yes. What does a vector field have to do with rate of change? What does a vector field have to do with rate of change? Is there anything we've talked about where a vector field has something to do with rate of change? What's that? Okay, if it's a gradient field, what does that have to do with rate of change? This is a gradient field. What's that? Of? Yeah, good. So if it's a gradient field, then the gradient field is kind of the representation of the rate of change of the z values on a surface. Okay? Because they're showing the direction of greatest rate of change. And then we know we can take like components of that to get any rate of change. That's the directional derivative. So a gradient field is essentially the rate of change of a multivariable function. Right? And that just goes back to what? Fundamental theorem of line integrals. Right? The fundamental theorem says, the total change or the net change in a quantity can be calculated bit by bit using its rate of change, right? You can accumulate little bits of change using the rate, and that's what the gradient of f is. It's essentially the rate of change of f. Okay? So then on the flip side of that, if you have a vector field, what is the rate of change of a vector field? What is the rate of change of it? So now think of a vector field. Doesn't have to be a gradient field. It's a function in and of itself, right? A vector field is a type of function. So the next thing we're going to explore is what is the rate of change of a vector field. So there's actually two kinds of rate of change. If you have a vector field, we look at two different types of rate of change, and the first is rotational rate of change. Rotational rate of change is the first of two types of rate of change of a vector field. And we already kind of saw this with Green's theorem. So what we want to do is we want to investigate a small element, dA of a region in D, of the vector field P, Q. So I'm going to highlight that in yellow. Okay? And then we're going to blow that up. Okay, we're going to make that big so we can talk about it. And so that dA consists of a horizontal change dx and a vertical change dy. That's our dA. And that little thing is living in this vector field. So here are the vectors of the vector field, really close to our dA. So I'm using the subscripts to say top, bottom, right, and left. So there's the bottom vector, the top, the right, and the left vector are the kind of the vectors in close, right around in that local region of this very small element of D. So according to the right-hand rule, counterclockwise rotation is positive rate of change. So positive rate of change will be the tendency of counterclockwise rotation. Counterclockwise rotation, spinning this way. Okay. So I'm going to take those four vectors that are in close to our dA and I'll show their components. And so we're going to ask which of those components are contributing to counterclockwise rotation of around in the spot. So what components of the vectors above and below vectors above and below and around, or above and below first? Okay, so we're going to look at F top and F bottom, and we're going to say what components of those contribute to rotation. So you got the horizontal components and the vertical components of the top and the bottom vectors, Ft and Fb. Which components of Ft and Fb contribute to spinning around this, rotation? What's that? Jorge says horizontal. Agree with that? What about the vertical components of those vectors? Do those contribute to spinning? Yeah? No, I'm talking only about the top and bottom vectors. So we're just focusing here on the top vector and the bottom vector and asking which components of those will cause this thing to spin. Yeah.
Would it be like the ratio between the two almost? Like if
Two.
one is more, it'll rotate.
But I'm asking which components, right? So there's the purple horizontal components and the green components. Which of those, purple or green, contribute to rotation? You still going to stick with horizontal still?
Yeah, because like if I was to push it vertically up, like
Yeah.
it wouldn't rotate like that. It would rotate like this or like shift up. But if I push it in this direction,
Right. Is that what you're going to say, Lane? The green. Do the green components contribute to spinning this? What?
The vertical one?
The vector just like popping away.
Oh. Sorry. Do the green ones contribute to rotation?
I would say no. 'Cause
No, right? It's just like pushing or pulling on it. Do you see that? But it's not going to cause it to spin. What about the purple ones? Those going to cause it to spin?
yes.
Yeah, it's like so if you imagine around this point, right? Think of it around this point right here. The purple causes spinning. The greens do not. The greens like push-pull. Does everyone see that? This is super important. This is the foundation of this idea of curl. All right, so now you get to watch again. So we don't want the green one. Let's see. Bye. And bye. Okay. Okay, so change in P is what, so the change in our, so that P is our horizontal component, right? Because it's PQ, F is PQ. Yeah, F is PQ. So that's the horizontal component. So how would you finish the statement? P changes by what times the change in Y? This is just our basic rate of change formula, right? So what goes in the question mark there? What would you multiply the change in Y by to get the corresponding change in P? What rate of change would go there? It's so easy, it's hard, right? What would you multiply dy by to get dp? Just kind of like solve for the question mark. Yes. So that would be the partial of p with respect to y, right? And that's what we call p with respect to y. That's what's just when we say this, right? That's just py, right? So from bottom to top is a change in y, and to get the corresponding change in our x component, p, which is what we're interested in for curl, it's just going to be the rate of change. P with respect to y times dy is going to equal to dp. Oh, now we're talking about the other way. Okay, so now, here's this next question came up. So what components of the vectors right and left cause rotation? So which components of the left vector FL and FR will cause rotation? Horizontal or vertical? Vertical, right? The horizontal components will just push and pull on that. But the green ones, those will cause turning about the center point. All right, so we've got some more fun animations here. So we don't need that, and we don't need that. So these are the four components that are going to contribute to turning. For a change in y, we want the horizontal components. And for a change in x, we want the vertical components. That's what's going to cause this thing to turn. So it's going to be the sum total of all that, right? So it's going to be the sum total of turning due to the horizontal components above and below and vertical components right and left. We want to sum all that up to get the total rotational strength, basically. But we have to take the opposite of Py because, look, so if for a change in y, if P is greater, then what direction of rotation do you get? Do you see how this is greater than this? Which way is these two going to make it spin? Do you see that the combined effect of those will create clockwise rotation? And because of that, we need to, counterclockwise is positive, so we're going to need to subtract the P component. But if you, for a change in x, if you have a greater vertical component, which way does that cause it to spin? Counterclockwise, which is what we want. So for positive change in y, if P increases, that's going to make clockwise rotation, so we got to take the opposite of it. But for a positive change in x, if you get a positive change in q, that's going to cause the counterclockwise rotation, so we'll take the positive version of that. So we need partial q with respect to x minus partial p with respect to y. Does that look familiar? What is that? Where do you say we've seen that before? Qx minus py. Green's theorem. Okay, so that's where that came from. This is the sum total of all the components that cause counterclockwise rotation. That's what we call the curl. The curl is rotational rate of change. Rotational rate of change. The strength of rotation at a particular point. Okay. Do you follow? But the curl, this rotational rate of change, is not a scalar, it's a vector. It's a vector. So what is the direction of the vector? So this is just the magnitude of the curl. This qx minus py is the magnitude of the curl. So if it's a vector, then it has a direction. What's the direction of the curl? To be consistent with everything else we've done this semester. But a vector points in one direction, right? So what's the direction of the curl? Anybody? Yeah.
Does it depend on what point the curl is coming from?
All right, so we're here in the screen. So this particular, so what direction is the curl relative to what you're looking at right here? Yeah.
Out of the screen.
Out of the screen. And why out of the screen? Is that what you're going to say?
Yeah.
Why out of the screen?
And it would be cross product.
Yeah, this is like cross product, right? So it's like when you turn in a circle this way, what's the associated direction? Like cross product, right? Straight out of the screen. Straight out of the screen. So the magnitude is the strength of rotation, and the direction of this is like this. That's the direction of the curl vector. It's orthogonal to the plane of the rotation, just like it was with the cross product. Okay, so that's the direction of the curl coming right out at you, and that represents turning like this in the plane of the screen. And then the magnitude of that vector is the strength of the rotation. So that would be k, right? That's k. So the curl of f, the vector, is qx minus py times k in this positive z direction.